So let's begin with the today's lecture of industrial pharmacy. So we are on to the pre-formulation, and these are the details that already we had covered in our previous lecture. We are on to the polymorphism. Now, what do you mean by polymorphism? Just I want to recall the things that the polymorphism, that is nothing but the phenomena of existence of a substance into the two or more different forms. And in this particularly, in the last lecture, we saw the polymorphism and its importance. While studying the importance, we had gone through a particular story of the Napoleon Bonaparte. I already explained. In order to just get the relevance and the flow, I will recall the things. What the story is, the story was related with the Napoleon Bonaparte when he tries to rule onto the Moscow. At that time, when they reached to the Moscow, at that time there was a difference into the temperature. So the kind of uniforms that the Napoleon Bonaparte and his army which had wear, that was consist of buttons, and these buttons was made up of a substance which is said to be the tin. And the tin that is existing, the metal tin that used to exist into the two different polymorphs. One is said to be the beta polymorph and another is said to be the alpha polymorph. And what is the difference between these two is that the beta polymorph, that is glittering white, whereas the alpha polymorph, that is dull white. And this conversion of beta polymorph to that of the alpha polymorph of the tin, that will occur because of the temperature differences. So in case of Moscow, when they reach, at that time there was a sub-zero temperature, right? So because of that, what happened? The color of the buttons that got changed to that of the dull white, and because of that, they thought that there is a change into the color. That means that might be because of some curse of the god, right? And because of that, they faced to a very pathetic defeat when they had fighted with that of the Moscow. Just at their gate, they faced to a defeat, and this is because of the not the curse of the god, but it is because of the conversion of this glittering white beta form of the tin into the alpha form. Particularly, the difference between these two is because of their polymorphic characteristics. It was the polymorph and not the wrath of the god. It is not because of the curse of the god, but it is because of the temperature differences. So the beta tin, as I told, that it is the metal, the alpha tin, that is the non-metal, beta tin, that is white tin, alpha tin, that is gray tin, beta tin, that is stable above 18 degrees Celsius, alpha tin, that is stable below 18 degrees Celsius. So this is having the tetragonal structure, that is having the cubic structure. So that is a quite interesting story. Whenever the study of polymorphism will come, at that time the story can be shared. So let's move to the different types of the polymorphisms. What are the different types? Based on the mechanism of the latex crystal formation. Broadly, the polymorphs, they had been categorized into the two different forms, into the two different classes. The first is said to be the packing polymorphism, and the second one is said to be the conformational polymorphism. What is the packing polymorphism? Packing polymorphism is the formation of different crystal lattices of conformationally rigid molecules that can be rearranged stably into different 3D structures through different intermolecular mechanisms. And when a non-conformationally rigid, that means the packaging polymorphism that is associated with that of the conformation, that means it is associated with that of the structure. The conformational polymorphism, these are not associated with the conformation, these are not associated with the structure. When a non-conformationally rigid molecule can be folded into alternative crystal structure, the polymorphism is categorized as a conformational polymorphism. Are you getting my point? What is the basic difference? The packaging polymorphism, it is related with the structural similarities, and the conformational polymorphism, it is not related with the structural similarities. That is the basic difference in order to keep in our mind, in order to remember. This is the example of the packing polymorphs, astron, that will show the three different polymorphic forms. The three different forms are the structurally similar one. So this is the form 1, this is the form 2, and this is the form 3. These three are the interconvertible. So what we saw the types of polymorphism. What are the different types? Packing polymorphism, conformational polymorphism. Conformational polymorphism, it is associated with the non-structural, and this is associated with the this is associated with the structural one. That is the packing polymorphism. Let's move through the different classification. The next classification, that is based on the thermodynamic system. Depending upon whether or not one form can transform reversibly or irreversibly to another with respect to the change of temperature and pressure. So here the transformation that will occur, transformation, that is the conversion, that is the change, reversibly or irreversibly. Reversibly we can take it back, irreversible, that cannot be reversed back, the change cannot be reset, and it is because of the differences into the temperature and the pressures. Now based on these, there are two different types of enantiotropic and the monotropic polymorphs. So what are the enantiotropes and the what are the monotrop? Enantiotrop, the temperature at which the two polymorphs have equal stability is defined as the transition temperature. In order to understand the enantiotrop and the polymorph, it is necessary that we must know that what is the transition temperature. Transition temperature, it will be represented as TT, that is the capital T, small t, right? The capital T, that is italic, and the small t, it is in the normal state. So the temperature at which the two polymorphs have equal stability, they will be having the same stability at different temperature and the pressures. Now here you can see that this is the transition temperature, and these are the two different polymorphs which will be having their two different uh, temperatures, melting temperatures, right? So this is for the first polymorph TM1, and this is for the second polymorph TM2, that is the melting temperature, and this is the transition temperature, the temperature at which they will get interconvertible, they will get interchanged based on the differences into the temperature and the pressure. So it is located below the melting point of both polymorphs. That is the enantiotropic. So what is the characteristic of the enantiotropic? The transition temperature of the enantiotrop that will remain below the melting point of both the polymorphs. This transition temperature, it will remain below the melting point of both these polymorphs. Or one polymorph can reversibly change to another form, one by varying the temperature and the pressure. So this is the reversible type. Changes into the temperature that will lead to the interconversion, and again the changes that can be reverted back based on the temperature and the pressure. So enantiotrop, these are the such a polymorphs whose transition temperature that remains below the melting point of the both polymorphs, and these are the reversible type of polymorphs. Monotropics, as far as the monotropic is concerned, there is a vice versa. So in case of monotrophs, the transition temperature that is located above the melting point of both polymorphs, that is the monotroph. In case of enantiotroph, it is below. In case of monotroph, it is the above the melting point of both the polymorphs. You can see here particularly the transition temperature that is above onto the melting temperature of first and melting temperature of the second one. So the change between the two forms is irreversible. In case of enantiotrap, the change is reversible. In case of monotroph, the change is irreversible one. So here you can see the basic difference. This is the enantiotrop. Just at a glance you can have, that is the transition temperature that is below, transition temperature is above overall to that of the individual melting temperatures. Now there is again a quite interesting story as far as the polymorphs are concerned and their interconversion. It is associated with the ritonavir. The ritonavir, it is particular the oral suspension, and that was produced by it is the product of the Abbott under the brand name Norvir. So in March 1996, FDA approved ritonavir and marketed as a semi-solid formulation. But 2 years later, in 1998, the batches began to fail in terms of dissolution test is concerned. A more stable polymorph was precipitating from the formulation. So this is because of what? As a result of which the Abbott has to withdraw the product from the market. So the Abbott had suffered to a huge loss. Now this loss is because of what? It is because of the conformational polymorphism. That is the stable enantiotrop form 2 was precipitated by formation of degradation product of the drug. So because of the interconversion of a product, see the significance of studying the polymorphism. If you are not studying it as such, if you are continuing with the API, and if because of the alterations into the temperature such things will happen, so that will be the huge loss to the manufacturer, the huge loss to the producers. Ultimately the future of producer that will be at stake. So that's why it is very important to study all the different polymorphs, and because of which the FDA that is made compulsion to study that one. So what we saw till now, we saw the classification of the polymorphs. How these are classified? These are classified into the enantiotrop and the monotrop. What is the enantiotrop and the monotrop? The basic difference is because of what? Based on what? The basic difference is based on the transition temperature. So in case of enantiotrop, the transition temperature that is below the melting point of both polymorphs. In case of monotrop, the melting temperature that is above the individual melting temperature of the, the transition. In case of monotrop, the transition temperature that is above the individual melting point of polymorphs. The enantiotrop that is reversible, the monotrop that is irreversible. Another polymorph which is said to be the pseudo polymorphs. Now this pseudo polymorph is what? It is because of the inclusion of the solvent or water. So the phenomena where solvent or water is incorporated in the crystal lattice or interstitial white spaces is termed as pseudo polymorphism. So what the pseudo polymorphism is? It is the incorporation, it is the inclusion of the either solvent or the water inside of the crystal structure or inside of the interstitial void spaces, void blank spaces, right? So that is said to be the pseudo polymorphism, and based on that there are two different types of pseudo polymorph. First is said to be the solvent, second is said to be the hydrate. When it is called as solvent, it is called as solvent when there is an inclusion of the solvent of crystallization. And when it is called as hydrate, it is called as hydrate when there is an inclusion of the water of crystallization. Now solvents, the residual solvents have been classified the ICH into three classes. What is the ICH? ICH, these are the guidelines given by the ICH organization. ICH, that will stands for the International Conference on the Harmonization. So based on which they had given the three different classes, that is the class 1 solvent, class 2 solvent, and the class 3 solvent. What is the class 1 solvent? These are such a solvents which are to be avoided. And what is the class 2 solvent? Class 2 solvent, these are the solvents which are to be maintained as a limited as far as their use is concerned. Whereas the class 3 solvent, these are the solvents with the low toxic potential. So the class 3 solvents, these are highly preferred one. Class 1 solvent, that not at all these are to be used. Now solvents to be avoided, these are said to be the class 1 solvents, and these are strongly suspected human carcinogens and causes environmental hazards. These are responsible for producing the cancer. So that's why these are to be strictly avoided. The examples are the benzene, carbon tetrachloride, and 1,2-dichloroethane. Class 2 solvent, these are the solvent which are to be limited one. These include the non-genotoxic animal carcinogens or possible causative agent. Their effect that is not onto the genitals. So the examples are the acetonitrile, cyclohexane, toluene, methanol, and NN-dimethyl acetamide of irreversible toxicity such as neurotoxicity or teratogenicity. The toxicity which is produced by the class 2, that is irreversible, that cannot be reverted back. Once it will happen, that means it will remain permanent there itself. They will be responsible for producing the neurotoxicity, that is the toxicity of the neural cells, that is in case of the brain. Teratogenicity, that means these are responsible for crossing the placenta and producing their effect in case of the developing fetus. The class 3 solvents, these are the solvent with the low toxic potential, and these are very highly used. The examples are the acetic acid, acetone, ethanol, ethyl acetate, and ethyl ether. Also included are the solvents with the low toxic potential to man are also included here. No health-based exposure limit is needed. So their exposure that may not lead to the any kind of the hazards to that of the human beings. Generally, when we talk about the solvents, the patent that is not granted, but this is the very rare case and the exceptional case associated with the Glaxo, where the patent was granted in case of the British patent to that of the use of trichlorofluoromethane or onto that of the chlorofluorocarbon. So what this study is, the use of solvents is not a usual practice because of the toxicity. It is interesting to note that according to the Glaxo's British patent, the crystal form of beclomethasone dipropionate used in the MDI. What is MDI? MDI is the meter dose inhaler. MDI is the trichlorofluoromethane solvent. By using the solvent, it was found that the crystal growth due to the solvation of the propellant chlorofluorocarbon was prevented. So here they had included the CFC, and this is the rare case. Hydrates. Now, what are the hydrate? Whenever there is a inclusion, whenever there is a involvement of the water molecules, that is said to be the hydrate into the interstitial spaces of the crystal lattice. So water molecule is present in crystal. The hydrogen bonding network contributes to the coherence of the crystal, and hence hydrates usually show slower dissolution rate compared to the corresponding anhydrate. So that's why most of the time we used to find the anhydrate forms, because the anhydrate form, these are quickly solubilizing. They will fastly solubilize, whereas the hydrate form, they will show the slower dissolution rate. Now, hydrates, they can be classified into the different subclasses. The crystalline hydrates have been classified by the structural aspects into three lattice sites. What are these? The very first is said to be the isolated lattice site. Water molecule resides in the crystal as isolate lattice. The lattice channel, that is the second class. Water molecule fills the space but not in contact with each other in the crystal. So this is the basic difference in the isolated lattice site and the lattice channels. What is the difference? The water molecule that will resides in the crystal as isolate lattice, whereas in case of lattice channel, the water molecule fill the space but not in contact with each other in the crystal. And the third one is the metal ion coordinated water. So the metal coordinated water in salt of weak acid, for example, nadochromyl sodium trihydrate. And here are some of the examples of the hydrates that are official in case of United States of Pharmacopoeia. The very first is the aminophylline, which is existing into the two hydrate form. Ampicillin having three different hydrate form, caffeine having one form, dextrose having one form, sodium acetate is in existence in three different hydrate forms. Hydrate can also exist in polymorphs. Yes, our whole study, our whole discussion, that is about the polymorphs. So the hydrate too, that is going to be existing into the different forms. Amyloid hydrochloride dihydrate is present in two polymorphic forms. By milling or compressing both forms, it was shown that form A was more stable than the form B. When the amyloride hydrochloride that is subjected to the milling and the compression, the two different forms was produced. That is the A form and the B form. The A form that is more stable and the B form that is the less stable. Moreover, it was shown that the anhydrate rapidly rehydrated to form a dihydrate on exposure to atmospheric relative humidity. RH, that will stands for the relative humidity. Now, what is the basis for the selection of the polymorphs? The polymorphs are selected on the basis of physical and chemical stability, the behavior to processing and formulation, and the biopharmaceutical properties. That is the predictive assessment of in vivo performance, how they will behave inside of the biological system. So how to characterize the polymorphs? As polymorphs, again, polymorph, these are nothing but the crystals. And as far as the characterization of the crystals are concerned, already we saw in our previous lecture. How we will characterize? We will characterize them by the melting point. We will characterize them by capillary melting and the hot stage microscopy, the DSC, differential scanning colorimetry, the detailed clip of this particular DSC we saw. As far as the thermal analysis is concerned, X-ray diffraction, how it is to be done, that also we already saw. And there are some of the miscellaneous methods like say the synchrotron radiation, solid state Raman spectroscopy, and the solid state nuclear magnetic resonance spectroscopy. Polymorph profiling. Now, how to profile the polymorphs? The characterize the different forms with the help of the X-ray powder diffraction, differential scanning colorimetry, thermoanalysis, microscopy, and the spectroscopy. If the forms have different properties like say the solubility, stability, melting point, then move to the next step. Other, no further testing is required. If there are differences as far as these three properties are concerned, solubility, stability, and melting point, and if this is going to be obtained through the characterization of previous methods, all these, then only there is need to go for the next method. So what is the next method? The next method is the if the drug product safety, performance, and efficacy is affected. If the drug that is going to be affecting safety, performance, and efficacy, then move to the step 4. Otherwise, no further testing is required. One can stop here only. But if there is a changes into these three parameters, safety, performance, and efficacy, then there is need to go for the step 4. So what is the step 4? Step 4 is the set acceptance criterion of the polymorphs content in drug substance with respect to control on the ratio of forms, dissolution, and stability. So that is leading to that of the characterization and profiling of the polymorphs. So what we saw as far as the polymorphs are concerned, here particularly the polymorph discussion is over. So we saw polymorph, its definition, we saw the significance of the polymorph, what are the different polymorphs, why it is necessary to study. We saw the two different types of polymorphs, packaging polymorph, conformational polymorph based on the structural differences. We saw the thermodynamic classification, that is the enantiotrop, monotrop based on the transition temperature, right? When it is below, it is the enantiotrop. When it is above, it is the monotrop. In case of the pseudopolymorphs, we saw the two different forms, solvents, hydrates. Solvents, they are of three different types, class 1, class 2, class 3. Class 1, that is avoided, class 2, that is limited, and class 3, that is used one. Hydrate, there is the existence of the hydrate polymorphs. Then the selection criteria for the polymorphism, the characterization of the polymorphism, and the polymorphism profiling. Now, after this, we have to go through the different points associated with that of the particle size. So, in case of preformulation, we studied the physical forms, we studied the polymorphs. So, these two characteristics we had studied, and their details already we saw. Now, the next parameter, next property is the particle size, particle shape, its distribution, its significance, and how the particle size that can be determined, how the particle size that can be characterized by different methods, like say the microscopy, sieving method, Coulter counter, and the laser scattering method. The laser scattering method, this is also called as the DLC method, dynamic light scattering. So particle size and shape, there is a great significance of the particle size and shape, and based on the particular dosage form, the specific particle size that is needed to be maintained. Now, particle size that should be in the range of 2 to 5 micron for the inhalation therapy. If we are going for inhalation types of dosage form, the particle size strictly it is necessary that it should remain in the range of 2 to 5 microns. The particle size there had its significance as far as the content uniformity is concerned. If the particle size is not uniform, that will not lead to the content uniformity. It will lead to the variation of the API into the different tablets. It will also affect the compressibility property, and that is what is the reason why we are going for the granules of uniform size, because of this significance of this particle size. The particle size, these are also responsible for the flow properties. Flow properties that can be improved with the help of the particle size and its shape in case of the tablet manufacturing. So particle size that will directly affecting the solubility and the dissolution of the rate. If we are going to be reducing the particle size, the surface area is getting increased. When the surface area is getting increased, the solubility that will be increased. When the solubility will get increased, dissolution will get increased. When dissolution will get increased, absorption will get increased. When absorption is more, that will lead to the better bioavailability. So particle size, they will ensure the drug content uniformity. among the dosage form and the compressibility. Particle shape affects the flow property and binding in tablet manufacturing. Particle shape is also related to contact points and hence the solubility. This is a very important one. The particle shape is also related with the contact point and hence the solubility. Because if we see the rounded one, there is a less contact point. If we see the cubical one, there is a least contact point. When there is a least contact point, then again the penetration is affected and that will affect the dissolution and further disintegration. Now some basic rules are there, like say for example, if smaller, that means the nearer or the quicker one to connect. Just take an example of two different balls. One is the football, another is the small ball. If we consider the football, in case of football, there is a difference into the center, or the distance is too much high as far as the center of both footballs are concerned. Whereas if we will go on reducing the size, that will leads to the reduction into the distance or the contact. Let's move to the interesting area, which is said to be the cooking or say the kitchen. In order to understand the polymorphism, the best example is from our kitchen. Like say there is the existence of a sugar molecule into the different kinds of the shapes and sizes. So this is the very well-known example that the sugar that is existing into the polymorphic characteristic. We will be having the powder form of the sugar, we will be having some crystalline sugar, we will be having still larger size crystals, and we will be having much more larger size crystals. So you know all these, right? So why this is? Because say if the particle size is getting reduced, it will fastly goes into the solution. So when the size is larger one, it will dissolve slowly. So it is less reactive and it will take a much more time. So the dissolution is late. If we compare with the crystalline form of sugar to that of the amorphous form of the sugar or the powder form of the sugar, so this will quickly goes into the solution. It will remain more reactive and it will take less time to form the solution and the dissolution. So again, in order to understand the particle size and its significance, just to see an example, if we divide how the surface area is getting increased. So with the help of this example, very clearly you can understand. Let's take an example. We'll be having a dice, a cube, a simple cube, whose whose size is it is the 1.7 centimeter side each. That means 1.7 centimeter from this side, 1 centimeter from this side, and 1 centimeter into its height, weight, and the weight. Now this has to be given three different cuts. One cut that will be horizontal, another that will be vertical, and another that will be transverse one. So this is the horizontal, this is transverse, and this is the vertical one. So when we will give a single horizontal, vertical, and transverse cut, we can see that we'll be getting the 1, 2, 3, 4, 5, 6, 7, 8. We'll be getting a 6 different cubes from a single dice, from a single cube of 1.7 centimeter or 1.7 cubic centimeter. Now this is the case when we will be getting the 8 number of the cubes in just single cut. Suppose if such single cut again we are giving, and if we are repeating the same for 24 times, now what will be the condition? Again, if we are giving, we will be getting much more. Again, if we are giving, so likewise we have to continue, we have to repeat it for 24 times. So larger number of particles are getting produced, larger number of particles are getting, their surface area is getting increased, and at the end of the 24 cuts we will be getting the total surface area of these small particles of 1 nanometer sizes. It is such that it will going to form an carpet area of a football stadium. Just imagine how much will be the size of the football stadium, what will be its uh, carpet area and how much amount of or how much small dice we took. Just a 1.7 centimeter cube, if we are subjecting it to that of the 24 time giving the horizontal, vertical and the transverse cuts, it will going to form such a number of particles which can cover the area of a football stadium. So that is from this example very clearly we can understood the significance of the particle size reduction and increasing the surface area. Now every time the situation is not like, say for example, if you are getting reducing the surface area, that means the solubility, dissolution and the absorption that will get increased or the bioavailability will get increased. This is possible, this is true only and only when the drug having its property hydrophilic one. If the drug is hydrophobic, this is not true. It will not increase the dissolution. Instead of that, it will affect the process of dissolution. So just to take an example of the aspirin is a hydrophobic drug. When you reduce its particle size, its surface area increases. Not all the surface area is increases. And being hydrophobic, its hydrophobic surface area increases. This is of most important. Being hydrophobic, its hydrophobic surface area is increases, and hence the water solubility decreases, right? So it is because of the inbuilt fundamental property of a substance. If the substance is hydrophilic, it will enhance the solubility. If the substance is hydrophobic, reduction into the particle size, that will lead to the reduction reduction into the solubility. So particle size distribution. Now, how we can go for characterizing the particle size and the shape? We can go for characterizing the particle size and shape by the different methods. So like say the microscopy, we'll be having the optical microscopy, electron microscopy, that is the scanning electron microscopy. Optical microscopy, just we will take the sample, we will observe it under the microscope and we can determine the shape. Mechanical, that is the sieving method. Electronic, that is the Coulter counter. Laser light scattering, that is the DLS, dynamic light scattering. And there are some of the miscellaneous techniques like say the centrifugation, air suspension, sedimentation, anti-sun pipette, recording balance and the PT, etc. Basically, these are very less. These are in use. Mostly, these are the method which are used one. At lab scale, there is a use of the sieving method. So, particle size techniques and the size range. Based on the particular size range, one has to go for a selection of a particular method. There are n number of methods. In case of microscopy, it is through the ocular micrometer, and electron microscopy for shape and size measurement of the particle. The particles, these are coated with that of the gold, and then their particle size and shape that can be determined by the DSC, differential scanning colorimetry. Then we have to go with the next method. So this is the sieving method. Sieving method, that is the quantitative method for the determination of the particle size and its distribution. So here particularly we can use it if the particle size that is larger than that of the 50 micrometer. As I said that it will consist of a nest of the sieves. So here there is a nest of the sieves. The sieves that are stacked one above onto the another. The coarse sieves that will remain at the top. The fine sieve that will remain at the bottom. And there is a collector system, collection